be all good to go, Sabir. People are joining, everything's on. I'll be back in a few minutes.
All right, thank you.
Welcome.
It's recording now, is it?
It is, yeah, I started the recording, it's 9 o'clock. I'll shave off the beginning of this.
All right. Okay. Can you hear me online?
Yes, we can hear you.
Hi, Kabir. All right. Okay, so today we're going to start a whole different topic in a way. So we spent a lot of time studying correlations in insulators in various spin liquids. And also talked a bit recently about fractional quantum Hall states, which are also similar to insulators in many ways. And I've surveyed a lot of the developments that happened in the last 20, 30 years in the field, and a lot has been learned. And the field is quite mature now. Of course, there are things that, few small questions here and there that need to be sorted out. But on the whole, the theory is in pretty good shape. However, original motivation for studying strongly interacting system came from the cupric superconductors, for example, where really all the interesting phenomena ultimately are in metals, not in insulators. And so we want to think about now the effect of strong interactions in metals. Now, we said a little bit about it at the very beginning of the course, when I talked about Fermi liquid theory, and the conclusion was that strong interactions don't do very much, that all they do is renormalize the mass of your quasi-particles and maybe give you some Landau interaction parameters that take strange values. But other than that, it's still a free Fermi gas. And this is sometimes we call the tyranny of the Fermi liquid. I mean, the Fermi liquid is a rather stable object, and it's found all over the place in the real world. But so the remainder of the course is really a way to now to start thinking about strong correlations in metals. And the simplest context is to take something we know well with strong correlations, which is spin system, and let's take a single spin and couple it to a metal. And that's what the Kondo impurity model is. This was actually understood even longer ago in the 60s and 70s. And maybe even, yeah. But I'll present it from perhaps a more modern perspective. And that will also allow us to talk about more complicated systems where you have strong interactions in metals, Kondo lattice models and Hubbard models, where now we know you can get interesting strong correlated phases even with metals, including some metals that don't even have quasi-particles. So that's sort of where the course is going to go, and I'll kind of end with that discussion of various models of metals without quasi-particles. Okay, so that's sort of where we are. So we'll talk about the very simplest case where we take the simplest system with strong correlation, which is a single spin, and couple it to a Fermi liquid, and that's what the quantum impurity model is. So quantum, it was actually discovered experimentally, the model that we're going to discuss, through some experimental observations by actually Miriam Sarachek, who just died a few weeks ago. So perhaps it should be called the Sarchi-Kondo model, but I think it's too late for that. Kondo solved it theoretically, at least understood the most important theoretical property of it. So you take a metal like copper. So you have some big metal, and this metal has electrons semi-liquid-like, and you put in a single impurity, a single site, say something like manganese, where there's a spin. Okay. So this spin will couple to the environment with some exchange coupling let's say there's some coupling, we'll call it J sub K. Okay, I'll make this all more precise and specific model shortly. But qualitatively, what would you expect? So if you have a single spin, the Hamiltonian is, well, just zero. It's got two, with a spin and a half, there's two degenerate levels. But if you put in a small magnetic field, a Zeeman field, let's call that H, it will couple to the spin this way. And what you measure is called the susceptibility. You look at the response of the system to this magnetic field, uniform magnetic field to a single spin. And that's a Curie susceptibility. And the answer you get, again, an undergraduate calculation that I urge you to redo if you haven't done it before, is S into S plus 1 over 3t. And for a spin and a half, this is 1 over 4. So that's the Curie susceptibility. It diverges as temperature goes to 0. On the other hand, the metal, the rest of the metal here, will have a susceptibility which is called the Pauli susceptibility. This will, of course, be proportional to the volume of the system. It's a single impurity. Chi Pauli is proportional to the volume, and as t goes to 0, and you get a factor of the density of states at the Fermi level. So this, as t goes to 0, goes to a constant. So the Pauli susceptibility is one of the signatures of a Fermi surface, because you have a finite density of states at the Fermi level. You have this picture. This is your dispersion. These are your upspin electrons and downspin electrons as a function of k. And when you put a magnetic field on, you change the Fermi level for the two of them. And it's this, the magnetization is the difference here, which is proportional to the density of states. And the magnetic field, basically, which gives you the splitting of the two levels. And that's how you get a constant susceptibility. So one thing you notice here is that the effect of impurities becomes very large as t goes to 0, whereas the effect of the metal is relatively small. And so even a small density of impurities is easy to observe. You just go to very low temperatures and you'll see the Curie contribution.
So this is the Pauli term is neglecting the or coupling to the orbital motion of the electrons. Or
yeah, so there's a diamagnetic contribution which has the opposite sign, which typically comes from far from the Fermi level.
yeah, I see.
So that is also a constant actually in a Fermi liquid. Yeah, okay. So sometimes you have to worry about it. Mostly, it's not as important. Yeah. Okay. Yeah.
I assume that the Pauli expression is at large V.
At large what?
At large V, at large volume.
Sure, infinite volume. We are going to talk about infinite volume.
So, but it might have order 1 correction, kind of finite size effect. How does that interact with the Curie kind, which is also order 1?
Yeah, so that's a subtle question. I don't think, then you'd have to really go into the Kondo model and study its finite size behavior.
But aren't you really interested in having a non-zero density of impurities? They're far apart, so you can treat them individually.
That's right. But eventually we're going to bring them closer together. Not this lecture, but we'll, yeah.
For today, but when you discussed observing it, when Miriam Sarachek observed it, she
Yeah.
had a lot of impurities.
Yeah, so there was a finite density, but still very small, 1% or even smaller. You can see that.
So that might be enough to control the finite size because they both scale linearly with the volume.
You have a huge sample. Sample is infinite. Let's just work in that limit for today's lecture. So V is infinite. But there is a finite density of impurity. So maybe I should multiply this by the volume times the density. So both contribution scale as volume, but there is a small number here. Okay, that's really what I should have said. So there's some density of these impurities, and there's a factor volume here too. And now we're just looking at the results per volume. E is infinite. And then even though rho imp is very small, you want rho imp to be small, so you don't have to worry about the coupling between impurities. So let's imagine rho imp is 1% or even smaller. Then you just need your temperature to be 1% of the Fermi energy. So this is roughly, V over the Fermi energy. Okay, I may have to, or maybe the number of particles over the Fermi energy, the appropriate units. Okay, so you want the temperature to be 1% of the Fermi energy, which is very easy. Fermi energy is 100,000 Kelvin, 10,000 Kelvin. So if you go down to modest temperatures, you can be completely dominated by this term. Okay. All right, so this is what you would expect when they're really far apart. And naively, so now the question really is, does this really work? So now we just have one impurity in an infinite sample. And the question is, does it still have a divergence susceptibility as temperature goes to 0? So this was not the first observation, but I'm not talking about history here. So what actually does happen, if you look at the impurity susceptibility. So the way you define this, if you're high impurity, is you measure the full susceptibility, you subtract the Pauli term, and you just divide by the number of impurities. The Pauli term is proportional to volume. This is also proportional to volume if the number of impurities scales with the volume. So you subtract out the Pauli term, which you know somehow, and then you look at impurity susceptibility. And we assume the impurities are far enough apart that we don't have to worry about that interaction. So then as a function of temperature, you would expect the Curie term just from this Hamiltonian. And you do see it. Now at low temperatures, different things can happen. If the impurities see each other, you could get some magnetic order. You get a freezing, a spin glass. In fact, this is how spin glasses were discovered too, when the impurities become more dense. But here, let's imagine they're really dilute. And then what you find, in fact, it doesn't diverge and saturates at some temperature. And so this temperature is called the Kondo temperature. And this chi imp, well, let's say is this, and you can use this as a definition of the Kondo temperature. So there's a low temperature scale, which is actually exponentially small in J, as you'll see. So at that point, the spin ceases to be free, and it's called Kondo screen. It becomes, effectively becomes an electron, as you'll see. I say that because the susceptibility is finite, and we view the Pauli susceptibility as like the signature of a Fermi system in the finite density states. So it sort of becomes Pauli-like because the spin becomes part of the Fermi sea. Okay. This also has the flavor, as we'll see, of confinement transitions. And this Kondo temperature is the analog of QCD, of lambda QCD, where you're going from here free spin-like behavior to some kind of confined state, which in our case will be the Fermi liquid. Okay. And so there's some arbitrariness in definition of TK, just like lambda QCD. Different people define it differently, but let's define it this way. Okay. All right, so, and in fact, if you want to look at this behavior here at low temperatures, there's a function here, which will be temperature over TK. Okay, and what we know today is that this is a universal function. It only depends on, doesn't depend on anything other than the fact that it's spin a half impurity. If it's spin 1, it'll be different, and so on. And so the aim of the theory right now is to compute this function. Today, of course, we can compute these things essentially exactly. but it took a while to understand how to do such things. Okay, so this function as t goes to 0 goes to a constant, it goes to 1. So whatever this function is, we define it as x to 1, and then also as phi of x goes to infinity, it has to match the 1 over 4t, so it must go as 1 over x. Okay. So there's some function that goes between 1 and 1 over x, which looks like this, and you have to compute it. That's the goal of theory. And today, you know, the work of Nathan Andre and others, we had exact Bethe-Ansatz equation, which will compute such things. All right. So that's one property of a Kondo model. The original property that was measured was the resistance minimum. And that also looks kind of similar. So you measure the resistivity of the sample as a function of temperature. So this is a bit more complicated because many other things contribute to resistivity, not just the spins. There's electrons interacting with phonons, or whatever it is, there's some resistivity in the pure metal without magnetic impurities, which normally would go in like this. So this is without magnetic impurities, without spins. So you measure this. I think maybe Miriam did something like this. You measure rho of t, and then you put in a few impurities, and then you see what happens. And what you find then is that the resistance changes. You know, it comes down, looks the same up here, but then there's some minimum, and eventually it saturates. So this part here is very similar to, you know, to that part. It's not the same function. It's a different function. So there's some excess resistivity. So let's say delta rho. Again, it'll be some function of T over T Kondo, which goes to a constant as over here, and then has decreases. So the effect of the impurity becomes much stronger at low temperature. So it's kind of the opposite here. Here, the impurity dominates at high temperatures, or the impurity susceptibility, because that's, you know, the impurity has a huge effect on the susceptibility. But if the impurity was just sitting there and decoupled from the system, it has no effect on the resistance. But at low temperature, effectively, the impurity becomes strongly coupled to the electrons, and that increases the resistivity of the metals. So what's observed then is the minimum. This is called the Kondo minimum. Really, this should be called the Sarachik minimum. And this happens again roughly at the Kondo temperature. Well, they're not exactly, because after all, where the minimum is depends on the background. Anyway. Okay.
So that's of order pk. It's not exactly equal.
Yeah, it's not the same. I mean, it will depend on what the background is.
And the function is not the same, right? It's a different
No, it's a different function. Yes,
Different function.
it's a different property of the same universal fixed point theory that can be, you know, this is related to some kind of T matrix of the quantum impurity. The other is just the thermodynamics. Yeah. Okay, so that's the background. And so the model we want to study is the following. So let's write down the Kondo impurity model. So I'm going to take the bulk, the copper atoms, say, put them on a lattice. I'll only draw one dimension of the lattice. But this is meant to be a 2 or 3 dimensional lattice. We're looking at it edge on. And then there's one impurity here, which I call the d electron. So these would be the c electrons. They have a spin alpha. And then I have a d electron sitting here. There's helping matrix elements T here. And we'll call this, sometimes called the hybridization. This is not the Kondo model, excuse me. This is called, well, the Anderson model, but there's so many Anderson models, so that's confusing, but it's really the Anderson model. I will derive the Kondo model from the Anderson model in 2-1. So the Hamiltonian is minus T, its neighbors, C there, I alpha, C J alpha. And then you have this site, epsilon D, and energy D dagger alpha, D alpha. There's a chemical potential, which is, as usual, I won't write it out. Then there's a hybridization, which couples the C and the D, the local impurity, which will be something like minus W times D dagger alpha, C 0 alpha. This will be the spin at this site. This is the site 0. Plus summation conjugate. And finally, to make this a spin, rather than another electronic state, we have to put in the local interaction. So there's U times ND up, ND down. So where ND alpha is just C dagger, sorry, D dagger alpha, D alpha. Okay, so that's the Anderson model, and this impurity model. There's another Anderson model, right? Yeah.
This is meant to be in one dimension?
No. You could do it in 1D, but the behavior in 1D is a bit more complicated. So let's say 2 and above. All right, so this is our, this is a 2-dimensional lattice and just one side. So if you look at it from the top, you have a lattice here. And there's an impurity site there. There's an extra orbital on that site, which is the manganese orbital, the d orbital. So now you're interested in the limit where U is much bigger than anything else, P and W.
So the impurity, so the underlying, the ambient space could be any number of dimensions. So 1, 2, 3. But
Let's say 2 and above, 2 and above.
And the impurity is always a point. It cannot be on a line.
That's right, it's a point. It's always a point, like in this picture. Or in space-time, it's a line. Okay,
Right.
So it's a line impurity in space-time. Yeah. And there's it's not a trivial impurity, it's got a dynamic degree of freedom on it. Which is because you have to add it's the degree of freedom that gives you the Curie susceptibility at high temperatures. Okay. All right, so that's the model we'd love to solve in this regime.
You do not allow it to hop. So is it pinned down?
No, it is hopping, that's the W. I
No,
can see it hop.
D. So the impurity can also move around. Or
Okay, so
I thought alpha is the spin index of the impurity.
right, so let's see, there's two different things. There's a manganese nucleus.
Yes.
The manganese nucleus sitting here does not hop.
Okay, good.
It does not move. But so that the presence of manganese nucleus just means there's an extra state here. There's an extra D state, which is this state. And the electrons can hop in and out of that state, for sure. Okay. Now, what makes this spin is the fact that U is much bigger than T and W. And this is very similar to the Hubbard model. If you go back, historically, of course, things came in the opposite order. But we talked about the Hubbard model and then showed that at half filling, it just became a spin because at large U, you put one electron there, but you were forbidden from putting the second electron. And that's exactly what will happen here. We're adjusting epsilon D so that this d orbital likes to have one electron. So let's see. So if I just take the d site, now maybe I should do this part before what I was going to do. So if I just take the d site, just the d part, there's only two terms in the Hamiltonian, let's call it HD. And the chemical potential, let's say, has been absorbed in the definition of ED. Okay, so there are 4 possible states on that impurity site. There's the empty state, which will have energy 0. And there's a doubly occupied state, which will have energy. So that's the empty state. There's a doubly occupied site. You have energy 2 epsilon d plus u. And there's a single occupied site that will be here. We'll call that epsilon d. That's 1 or this. So naturally we want epsilon d to be, I hope I got this right. Sorry. Sorry. 0 and 2 epsilon d plus u. And here's the singly occupied site, this or this, which will have energy epsilon d. And we are assuming that this is much below that. So a typical value would be epsilon d is of order minus u over 2. That's the particle hole symmetric case. And these two become degenerate, but it doesn't matter, they're way up there. And you've got a spin sitting here. So, as we discovered in the last month or so, once you have a spin with this constraint of single occupancy, all kinds of novel things can happen, fractionalization, spin liquids, anyons, and so on. And we are hoping for such similar fractionalized phenomena here, although in this particular model, they don't happen. But there's still an interesting regime, a crossover regime where it's as if things are fractionalized, which is again not dissimilar from QCD.
Is there any reason to think of this D particle as actually one of the electrons from the manganese atom?
Yeah, absolutely. That's what it is.
That's the picture.
Yes. Yeah. So, I mean, the picture is that the matrix has some sort of on the conduction bands, which are S and P and D orbitals, but manganese has those plus an extra electron. So, which is why I just added as a second side. I mean, there's a very precise way of doing the band structure and deriving actually all the numbers model. I mean, really all you need to know is the spin of the impurity. That's a well-defined number. So if the spin is a half, at low energies, there's nothing, this is all there is to it. There's only one number you need to know, the W. Compute.
The orbital spin of the electron of the manganese atom matter. So for example, you could have
it could matter. So if you had degenerate levels, then of course you will also, the spin could be different from spin a half, but if it was Bohn's rule, you would get some maximal spin. But you could also have orbital fluctuation, then you get multi-channel Kondo problems. Yeah, so that would be more, that would be another index on D other than the spin.
so that's a natural way to get the multi-channel. Or just
I mean, that was the original motivation. I think experimentally, because the orbitals are not exactly degenerate, there is, and that breaks all the multi-channel, exotic multi-channel effects. I think there have been other realization of the Kondo problem in semiconductor heterostructures, where the Kondo degree of freedom is not spin, but the spin is that you hit like the orbital index, so you're guaranteed to have degeneracy. So there's been actually some very beautiful experiments by Dan Ralph and David Goldhopper-Gordon, actually, where they have seen multi-channel Kondo effects using gates. So basically, a quantum dot also is like a quantum Kondo problem. That's a more recent realization of this. Yeah, but in well, there have been some, but not entirely convincing claims that in higher spin or higher orbital impurities in metals, that there's multi-channel quantum physics. Okay, but that's getting sidetracked. All right, so you got a spin. And so in the large U limit, we can do what's called, in this context, it's called the Schrieffer-Wolff transformation. But that's exactly the transformation we made to get the Heisenberg exchange model from the Hubbard model. And as we're doing this in the opposite historical order, all of this was done before all of the work on the Hubbard model. So it's not as obvious as it seems now. So what we're going to do is we have this impurity here, and this impurity is coupled to some conduction band. There's some whole bunch of energy levels here. And now what can happen is that this electron, for example, can go from here to there. So when it goes there, this level will move up here because it's empty. And then what happens? Yeah, so it's become empty. And then it can come back as a spin down while flipping the spin of the conduction electron. So basically, you can flip the spin of this electron while flipping the spin of the conduction electron. Okay, so that's a second order process. You want me to draw it more explicitly? So this electron, so there's two possible states. It's spin down, the spin down goes up here. So you have an extra spin down sitting there. And then you take an electron with spin up here and you bring it down here. So you're left with a spin up electron there, spin down electron there, and you have a spin up electron here. So the impurity spin is flipped and also the conduction electron spin is flipped. So that gives you an exchange coupling, very much like in the Hubbard model, almost exactly the same thing happens. The difference was in the Hubbard model, you got two sites with exactly the same level structure. Here you have an impurity spin with some Fermi C. Or really, as you can see from here, is the site 0. Okay. So now I can write down the Kondo model, which is closely connected to this. The bulk system is exactly the same. And that whole mess under these conditions where this level is much below these two will give you the Kondo Hamiltonian. And I'm sorry, so to be consistent with all my notation in the notes and various other things we'll do later, I'm going to call this U sub D. Okay. So what you will get is the Kondo interaction. Okay. Yeah, so it is just J Kondo, and to second order, it's the impurity spin, which I'll call SD now. SD darted into C dagger 0 alpha, sigma alpha beta over 2, C 0 beta. And here SD is just exactly 1/2 D dagger alpha sigma beta theta, and J Kondo is the following. It's 2W squared and 1 over minus epsilon D plus 1 over epsilon D plus U. So these two terms come from the reverse process. Here you have a spin down, say, then it can happen in the opposite order. You can take an electron from here, pick a spin up electron, put it here, then you get a doubly occupied site. And then one of these can go back. So you'll come back down here with a spin flip. Okay, so those are the two energy denominators. And this is to second order in W. Now there's also another term which is often neglected, which is something like V times C dagger 0 alpha times ND up. There's ND down. It's like a density-density interaction. We just ignore it. It's there, but it doesn't do much. The important term is the Kondo exchange term. Okay, so this is our Hamiltonian that we'd like to study. And what Kondo did was perturbation theory in JK. He computed resistance to second order in JK. To second order in JK, you just get temperature independent contribution. So you have to go to third order in JK. So it's sort of like a two-loop graph. And when you evaluate it, you found a logarithmic dependence on temperature. And that was an indication that something is becoming larger. Okay. And this is again analogous to QCD, where if you compute the gauge coupling constant, you find normalization, which are logarithms. Okay, we'll do some of that in a few minutes. Yeah.
So conceptually, if you start from H, what exactly did you do to get to HK? Did you integrate out anything or?
Well, you should view it as a canonical transformation. So we talked about this at the beginning of the course. You do a canonical transformation where you eliminate W. So you define a new Hamiltonian. So roughly speaking, HK is H times some U dagger. Okay, so that's what it is.
When you say you integrate out those two levels, that,
You could say that, I mean, but it's, if you want to do it exactly and not generate time-dependent terms, you have to do it this way. If you want to use the Hamiltonian picture, this is what you have to do.
But you still have the D's, so you didn't integrate out the two levels.
Well, yes, but there's a constraint now. D dagger alpha, D alpha is 1. So these are not really fermions anymore. They're constrained for
perhaps in this last term, you could set ND up and plus ND down equal to 1, right? To be consistent.
Yes, in fact, yeah. So there is, yeah, you're absolutely right. So this is correct. So there's a potential scattering term. Yeah, that's just, thank you. And that's what caused the confusion.
I mean, if you do this by doing Will-Wigner perturbation theory to get the effective Hamiltonian in the degenerate subspace, that Hamiltonian is energy dependent. Okay. And this canonical transformation is equivalent to sort of getting rid of that energy dependence.
Let me.
It's negligible in the large U limit, right?
All right, let me just say that since it was many months ago when we did this, I thought I corrected it, or maybe it was a homework problem. So right now, you know, you can view you have a big Hamiltonian, whose Hilbert space has been split into 4 sectors. So there's really 1, 2, 3, 4. So you can divide the whole Hamiltonian into 4 sectors. And in this sector, you have spin up on the downside here, you have spin down on the D side, you have an empty side, and you have, okay. So this is our Hamiltonian, and you have all possible infinite number of states of the conventional electron in each block. But the state of the D spin is specified. And so this, however, this W sitting here, where's the W? Here, has off-diagonal contributions here. There's various W's here. All the W terms connect these sectors. So if you take you out of singly occupied state to W occupied. So you do a canonical transformation. You choose your U so that all of these W's in the new Hamiltonian, in the H Kondo, these are gone to second order W. Actually, these don't go away, but no, sorry. Yeah, these blocks go away. So now you have a reduced Hamiltonian in this block. You can forget about those terms. And that reduced Hamiltonian is that one. And the W's are here, sorry, they're not here. All the W's are here. Okay, so there's no W. We've gotten rid of this at a price. The price is that you have a constraint, but you've gained a lot. You've gained in the large U limit, you have a coupling constant J, which is small. since U is going to infinity, JK is small. It's much smaller than any other scale. And so you might think, okay, all's well and good. I have a small coupling. I can just do perturbation theory in it. And that's what Kondo discovered, that you can't. Because, and the reason you can't is because you have a gapless set of states to also deal with. Yeah. Okay. Great. Well, yeah, maybe this is just the way the discussion is going. I'll do it in a different order than the notes, might as well. So let me just go ahead, since I've prepared the ground, to describe a little bit about Kondo's calculation. Okay, so what Kondo computed in today's language would be interpreted as the RG flow of the Kondo coupling. In fact, that's what was interpreted by Yuval and Anderson. And this was really the very early days of RG before Wilson even entered the game. Okay, so what Kondo computed was let's just say we are field theorists. We don't know about RG, but we know a little bit about field theory, is the renormalization of JK. Okay, so we have we have this constraint on the d dagger d, and this makes life difficult for us in the sense that we can't think of d as a free fermion or even the spin as a free fermion that obeys the Higgs theorem. But it's not really much of a problem because we can evaluate the perturbation theory, time-ordered perturbation theory, without using Higgs theorem, just by actually explicitly looking at the time-ordered correlation function. Right, so you take your partition function, which is the trace of e to the minus beta hk, and then you can write it as some expansion of various time-ordered correlation functions. You have some c's, c dagger, you have various s's, and so on at various times. Ones like this, it just expand the whole thing out. And you have some integrals over times. These will have various times, and there'll be a time ordering symbol. Okay, lots of indices here that I'm dropping. So the usual trick when you do Feynman diagrams, when you get a multi-point correlator like this, is you use Higgs theorem. But here, you can't use Higgs theorem on the S's, but you can on the C's because this is an expansion where we think of HK as H0 plus some interaction. And our H0 is just free fermions. Oh. Okay. So this part, we have a very simple Hamiltonian from which we can do time-ordered perturbation theory. For the spins, well, the Hamiltonian is 0. There is no pure spin Hamiltonian. All of the Hamiltonian is in the interaction field. So actually, let's see. It's typically for this to be consistent to have 4 C's and 2 S's. And so this is a term of order JK squared. So we're just doing perturbations here in JK. And so you get 4 C's and 2 S's. So what do we do with this? Well, since the free Hamiltonian, the spin and the electrons decouple, we can go ahead and apply Higgs theorem here. Okay. And then what about the spin? Well, the only thing the spins we need to know from this time-ordered expansions, they come at certain times, say tau 1, tau 2, and they have some indices, A and B. So the only thing we need to know from this time ordering symbol is the ordering of the spins. Does A come before B or B come before A? So this thing, depending on where we are in integration, will be either trace SA, SB or trace SB, SA. So all you need to do perturbation theory to any order you want is to be able to evaluate traces of spin operators with the free Hamiltonian, just trace. So this, of course, we know what this is. This is just delta AB over 3 S into S plus 1. So when you get 3 or 4 of them, things become a little more complicated, but not too bad. You can evaluate all the traces. So basically, once you know the traces, and once you know how to do Higgs theorem, you're done. You get an exact expansion to any order you want of JK. All right. So, okay. So it's not as scary as it looks. It's really doable, even though there's no Higgs theorem. And in fact, there's a nice way to represent this. Since there's nothing much happening on the spin sector, except the ordering. So you just imagine that you have, here's our time running this way, and the spins are sitting here. So there's a spin and here's a spin. And every time the spin acts, there's a JK, and there'll be a spin operator on those points. And then you have the electrons moving around. And so you'll get various graphs like this. So these are the electrons. You get a graph like this for some Kondo interaction term. And then you will also get this graph. So this one with the opposite order. Sorry. Okay, things like this. And and this graph is not exactly the same as this for various reasons, including the fact that the spin ordering is different. This spin comes before that. As far as the spin up matrix elements of the conduction electron is concerned. If this is your real time, and then the spins of the conduction electron operators come in the opposite order. So the fact that the spins don't commute, that the SU2 algebra is extremely important. It's only the non-commutativity of different spin components that leads to something non-trivial. Okay, so that's a sketch of the calculation. The actual calculation is in the notes. You can see it. And you can just see right here, what we are computing is the zeroth order term with just one spin with the conduction electron coming in like this. So this is JK. And these are the two contributions at order JK squared to the renormalization of JK. Okay. So if you compute this, which is done in the notes, and you get the famous, and in terms of you get the following result, which is what Kondo did is set finite temperature in a more complicated calculation because he directly computed the resistivity. Here we're just thinking of the renormalization of JK. That's the bare term, these are the renormalization terms. And so what you get is that something like this, JK normalized is JK, that's the bare JK, plus JK squared, and then you get okay, integral over the density of states of the conduction electrons, rho of E, over basically mod E with a factor of 2. This is at zero temperature. Here. Yeah, so what is rho of E? Rho of E is 1 over volume, sum on K, delta of E CK. So that's the EK is the dispersion relation of the conduction electron. Okay, so this is what you get from second order in the Kondo coupling. All right, so this, the only trouble with this integral is it's divergent. There's a log divergence because rho of E, we're just going to replace rho of E by a constant, which, whatever I call it in the notes, sorry, in the notes I call it D of E. So let's stick to that. So we just replace D of E by D of 0. Because typically the Kondo, all of the interesting physics is happening at energy scale much below the Fermi energy. The Kondo couplings are much smaller than the Fermi energy, and so on. All right, so this is divergent. There's of course an upper cutoff of some type. And there's in the physical system, there'll be some cutoff, for example, temperature. If you try to do this at finite temperature, so you get a finite answer, which is what Kondo finds. So what you find then, roughly speaking, that JK normalized is JK there, JK times 1 plus, the coefficient is precisely determined. And I hope I got it right. Yeah, I think it's fine. So there's two contributions here from, sorry, I should really make this, get rid of the 2 now. This is only for positive energies. So 1 plus JK log of cutoff over temperature, say. And there's a D of 0 here. Okay, so Kondo computed something else, but this is what he found, that there was some bare quantity, and then the correction was 1 plus JK times the density of states and log of some cutoff over temperature. Okay, so what does this tell us?
Sign is plus because it's second order perturbation theory. Is that?
Well,
That's
the
important.
coupling is increasing. So as you're going to low temperatures, the RG flows
But
to
the
large.
reason that happened in this calculation is because it's second order perturbation theory.
No, I don't think so. The fact this is plus?
Yeah.
No, I don't think so. I think that relies on the spin commutation relations.
I see.
It comes from commutator of spins. Yeah, well, for example, I mean, here JK is positive, meaning your interactions are anti-ferromagnetic. If JK can be negative,
I see.
then the flow is in the opposite direction. So if you have a ferromagnetic coupling, then the coupling goes to 0, and that's why there is no Kondo effect there. Okay, so what we notice here is that the correction becomes about the 0th order term. So this cannot be trusted. This is the physicist's way of deciding when a theory is not convergent. Just look at the first term and see when it becomes about the 0th order term. So this cannot be trusted for T less than some Kondo temperature, where the Kondo temperature roughly is about a J times exponential minus 1 over D of 0 and J. So I'm assuming J is positive, sorry, JK.
Lambda in the first term.
Yeah, okay, lambda. We don't know what lambda is. Of course, you need to go to 2 loops in next order to get the prefactor correct. There's complicated stuff there too. And this has been done to very high order. But at 1 loop order, we can't really say anything about the prefactor. But we can say that this is in fact exact, the term in the exponent is exactly this number. Okay, so we're getting some divergence in our perturbation theory because of very low temperature effects. So what Kondo said was, this explains the minimum. So what Kondo could say there, well, things are increasing, so maybe there's a minimum. And this is the Kondo temperature. This is resistivity. But what Kondo couldn't say is what happens now. What happens at
Why did he explain the minimum?
well, because this is a term that's becoming larger. It's become, so the resistivity of all the other terms of resistivity decreases the lower the temperature. Here you're getting a term of the resistivity that increases the lower the temperature.
But you
So
have
have two terms.
Impurity pushes it up, it might be pushing it down.
No, pushing it. Yeah, it shows it pushes it up. Yeah. It may not be a minimum, it's true, it could be. Yeah, but okay, so Kondo didn't prove it is a minimum, but it's a possible explanation for a minimum. And beyond that, he couldn't say. I mean, in fact, this thing just blows up as t goes to infinity. Maybe the resistance goes to infinity. In fact, it doesn't. This term goes to infinity as t goes to 0, which would suggest the resistance would be infinite. It becomes an insulator. It doesn't, it saturates. And that requires more sophisticated analysis than Kondo was able to do. Okay. How it saturated wasn't understood much later in Wilson's numerical RG and also in Nathan Andre's Bedriant's solution and so on. That was required to then understand the really low temperature behavior. So as I said, this has a alternative interpretation in RG, where you imagine taking the cutoff and reducing the cutoff. So you go from lambda to lambda minus 2 lambda. And then you say that use this notation that lambda minus d lambda lambda times e to the minus dl. And then you get a different, you can write this as a differential equation dkk dl with rho of 0 times d of 0, sorry, times jk squared. Yeah. And then all our ignorance is in the higher order terms, dkq, many of which are known today, of course. Okay, so this is the world's simplest RG, but also the most important. So as you go to low energies, there's flow to very strong coupling. So this is telling us that as you lower the temperature, go to low energy scale, things fall apart. And JK, all kinds of things could happen here. We don't know. There could be a critical point, another fixed point. That's what happened in the multi-channel Kondo case, or go all the way to infinity. And what is the behavior of the system when JK is at infinity? Well, we can discuss that in a minute. Okay, so is that clear?
Is it the perturbation series in this case has a finite radius of convergence? No.
Radius. I don't think so. You mean here? I mean, just like QCD, I don't think it does.
So it doesn't.
Yeah. So yeah, that was going to be my next remark. This is exactly the RG equation for lambda QCD. For the gauge coupling also in QCD. Of course, in the field theory literature, it's written in the opposite way. They say that when you go to very high energies, things become free and the gauge coupling becomes 0. So that's asymptotic freedom. And at very low energies, you have confinement. So this is the asymptotically free fixed point, and who knows what happens on the other side. So you really have to figure out what happens at large JK. And I would say Wilson in his numerical denomination group was the first one to figure that out. Later on, there were more exact methods used. And what Wilson showed was that it goes, in fact, to infinity all the way. Okay. And so now we can, what is the behavior of the Kondo Hamiltonian at JK equals infinity? So you can go back to the Hamiltonian and see actually it's not so bad. We can figure out what happens here just by a new strong coupling analysis. Okay. But this analysis by itself doesn't tell us that this is the simple flow all the way to infinity. So you have a new fixed point here, and we have to do an analysis near this fixed point. Okay, so let's go back to our Kondo Hamiltonian. Yeah, so. Okay,
Question.
yeah,
So if you, all your goal is to understand this Hamiltonian, then I understand the logic of
mhm,
such small and it grows.
yeah,
But you started from another Hamiltonian, which had W.
yeah,
There was
yeah,
a truncation to get to this one.
yeah,
Now, what is not clear is whether, in that truncation, JK was small.
correct,
So
correct.
is it valid to take JK to infinity in this Hamiltonian rather than considering the original?
I think it is,
It's
yeah.
not the same problem.
It is not the same problem, right? So JK, you may remember, was W squared over U. So if JK is going to infinity, that's sort of like U going to 0. And U going to 0, we understand. That's just free fermions. And in fact, now that's exactly the conclusion we'll come to by looking at this Hamiltonian, that apart from some potential scattering, it looks like this is just free fermions scattering of some potential impurity.
So why didn't you do that from the start?
Well, because I can't justify that at large U. I mean, remember the JK going to infinity, that's in some rescaled energy units. You know, every time you do the RG, you're rescaling your units. So it's infinity, but it's really infinity with respect to the new cutoff. The reduced cutoff, lambda has come down to a very small value. And now JK is about the cutoff. So the original mapping was done when the cutoff was much larger. So it's a different problem at this point. So this has been strongly renormalized as a cutoff here, which I'm not writing down. But so it's not immediately obvious that JK goes to infinity is the same as U goes to 0. We have to analyze this separately. Okay, so but that is in fact the answer. So and it's easy to see why. All right, so now we really want to look at it in 2 dimensions because the 1-dimensional case will be different. In the JK goes to infinity. So let's say where's our origin? This is our origin site here. So what are we going to do when JK is infinity? Well, this d spin will just take one electron from the Fermi C and form a singlet with it. Okay. So on this site, say that's the origin site, I'll get a state which will be 1 over square root of 2. C dagger 0 up, d dagger 0 down, like C dagger 0 down, and d dagger. These are in one side. Okay. So I'm going to get, you can't see the red very clearly, but anyway, so that's a spin singlet between the C electron and C0 electron with D electron. And that's singlet's going to sit there. Okay, so there's an infinite Fermi C, so you peel off one electron. Now, if you had a finite size system, I have to worry about that. If one electron disappeared, it's going to change my boundary conditions and so on. But let's not worry about it for now. If you want, the conformal field theory, that's the crucial effect, in fact, when you write down the theory of the quantum. So you peel off one electron, and now this thing is a spin singlet. And there are some excited states here. There's a triplet state, which will be excited by some of these terms. You remove an electron or something. But the moment you excite it, you're going to pay an energy JK. So you don't want to excite it. It's just a vegetable sitting there. Okay. And so for the rest of the electron is concerned, this is exactly like forbidding electrons from going there. So I can replace this term by the term from V, C dagger 0 alpha, C0 alpha, Sn V to infinity. I'll just have a hole in my lattice. It's just a potential term. the spin has formed a singlet. And if I want to break the singlet, I have to pay a large energy, so I don't want to pay that. I still have a lot of gapless excitations. They will scatter off this impurity, but that's all. And that I can do. I can solve the problem of this free electron scattering of an empty site. Yeah, that's going to be exactly solved. In fact, we'll get to it in a minute. And so our conclusion is that in the end, there's no spin left, and it's just a slightly normalized Fermi liquid with a missing site. Okay. So that allows us to conclude, for example.
I'm still behind.
Yeah.
The index K on the C in the first one, on the first term is a momentum index.
Yeah, sorry. Yeah.
And the index 0
Is a site
is
index.
a site index.
Yeah, if you feel better, let me just.
So it's not just, this is just one of the Ks.
Yeah, I should have, absolutely. Okay. There's also, when you go from Ks to zeros, there's factors of 1/squared of volume that you could keep track of. But yeah, they all fall out. Yeah.
This analysis doesn't enable you to calculate the limiting resistance at t equals 0.
It does. I mean, up to a constant, it will allow you to.
It's finite, but there's something.
Yeah, so there's a precise way to do this, which is done by Nozier, where you look at, well, this will give you some zero temperature, some finite constant resistivity. So from now you know, for example, the plot the resistivity. So Kondo told us it started to go up. This analysis told us it goes to a constant. So this impurity only gives you some constant. And now you want to connect them up, and you can do high order perturbation theory that will allow you to go a little bit better here. But you can also start doing this here. And that requires you to put in other leading irrelevant operators. This is a relevant operator, but there are other operators that you can write down. So that was done by Nozier, I won't do it. And then putting new operators here at the strong coupling fixed point, you can figure out the temperature dependence of it. But of course, that each operator comes with a new unknown coefficient. Then to get the whole function in the limit where the bare JK is small, you need two more. You need to solve the full problem. And that's what Najan did, where you can get the full function, including the coefficients of all the leading operators, irrelevant operators, all expressed in terms of one unknown, which is TK. I think in QCD you do very similar things, right? That's heavy quark perturbation theory or something like that. No, not quite, but there are very strong coupling expansions in QCD.
We need the Nathan Andre that solves the.
Sorry?
We need
Yeah, we need.
Yes, yeah, right.
I believe it's not interval.
Yeah, it's chaotic. Okay. All right, so I think I've covered the basic phenomenology and the basic RG equation without actually doing any serious calculation. Any questions? I mean, the Kondo calculation is fun to do. It's in my notes. You can do it in many different ways. Yeah, everyone should do it once. Yes.
Actually, I have one question. If you went back to the Anderson model,
Yes.
you could guess in view of this answer that we could get the same thing in the Anderson model by setting U and V to 0. And then instead of having an electron vacancy, we have an extra electron.
Yes.
We have to solve that. But I suspect it flows in the infrared to the same thing as a shared vacancy.
Yeah, so basically this says that small U perturbation in the Anderson model is stable, which it is. So you could do small U perturbation theory. And this effectively, small U perturbation theory is like a large JK series, whereas this ultimately is a small, this whole RG flow is only believable and it's only universal when JK, the bare JK is small. Because then it's only the RG flow right here that's universal. once it gets strong coupling. If you start with a large bare JK, there could be other relevant operators you do have to worry about. So there's I think, yeah, there's a matching of the terms order by order in 1 over JK and small u, but I don't think there's any quantitative connection.
But I think with putting u equal to 0 in the Anderson model would be similar to going to lattice QCD at strong coupling.
And it gives you qualitative.
Yeah, it gives qualitative. Yeah, that's
Yeah, so these questions actually become much more relevant and interesting when you talk about the lattice, Kondo lattice model, which probably I won't do today. Yeah, in fact, I won't. And there also, it took a while to understand that the Kondo lattice model. So when you take the Kondo lattice model, small u perturbation theory has a lot of nice features. You can prove things like Luttinger's theorem to all orders in U. You can prove all kinds of things for the lattice, Kondo lattice, for the, yeah, okay. In the Anderson lattice model, you can prove all kinds of things to all orders in U. And to see how that emerges from the Kondo model is highly non-trivial. Because in particular, so this is going to be a major topic of various future lectures. So if you took the small u perturbation theory of the Anderson lattice model, it would tell you that the volume of the Fermi surface includes the density of d electrons. Whereas if you start from the Kondo lattice model, that's highly non-obvious because the d electrons don't even move. Should that have a large Fermi surface or should it have a small Fermi surface? And the answer is actually both are possible. So in the lattice model, there's another phase possible with a small Fermi surface where the small u picture doesn't work, but there's another phase where the small u picture does work. But this problem is kind of simple. The small u picture always works. And because JK always flows to infinity. I mean, for the multi-channel Kondo problem, for example, you could never use a small u picture because you flow to a fixed point. That's a finite JK. Okay. All right. So what I want to do now is actually do a calculation, which is very much in the spirit of the calculation we did for spin liquids. It's a kind of a large M calculation, which has the virtue of reproducing all this phenomenology, almost exactly correct. So all the way at all temperatures. So in a 1 over n expansion, you can compute the whole thing and hope that it applies for n equals 2. In fact, in this case, it does pretty well. But it has a secondary advantage, which is the real reason for doing it, which is that it generalizes to the lattice problem. But you have infinite number of impurities, not just one. So let's talk about that now. All right, so we're going to look at the same Hamiltonian. And we're going to turn the crank by all the fancy methods you've learned in studying spin liquids. So what we're going to do is we're going to introduce spin-ons, and I'm going to call them F rather than D now, because just to emphasize that these are not electrons. And there's a constraint, F dagger alpha. If alpha goes this one. Okay. So now you see immediately there's a U1 gauge symmetry. Which is F alpha goes to F alpha into the F phi of tau. There's only time, there's no space in this gauge symmetry. Well, this is kind of a trivial gauge symmetry because there's only time, so there's no flux. And you can always choose a gauge where you can get rid of it. Although there's some subtleties with periodic boundary conditions at finite temperature, you can't quite get rid of it. Okay. Anyway, so we kind of try to use the gauge language now, which is using a sledgehammer to crack a nut, but it's because the same language will be much more powerful later on for more complicated problems. So we want to ask now, you have a U1 gauge symmetry, and what is its fate in the low temperature limit of this Hamiltonian?
Sorry to interrupt, but the F's are the same as the D's in the Anderson.
The D's in the Anderson model didn't have a constraint, so
Well, okay,
yes.
doesn't have a constraint, but
Yeah, so I just for future purposes and to really emphasize that these are not electrons, I'm calling them F. But I should have called them D, but I'm changing notation. Yes, that's all.
But they are anti-commutative. They're still anti-commutative.
Oh, yeah, yes, yeah. But there's only one side, so. They're certainly anti-commute with the C's and so on. Okay, so where we're going with this is we're going to find, in fact, even a closer analogy to QCD, we're going to find that the strong coupling state, in this case, is a Higgs phase, where this gauge symmetry is Higgs. So it's like a confining phase. And it's that confinement, which is the essence of the Kondo effect, where the spin is screened by the conduction electron. They're kind of confined to each other. The spin-on becomes an electron by a Higgs phenomenon. All right, those are just words for now, and you can just discard them if you don't like them, but they'll become useful when we talk about the Kondo lattice model. All right, but let's just go forge ahead. So the first thing we're going to do the large N expansion, you can rewrite this term as we've done before. Yeah, so this term is minus JK over 2 F dagger alpha C0 alpha and C dagger 0 theta F theta plus some constants, not important for us, where alpha and beta go from 1 to 2. But now I'm going to go from 1 to m. I'm going to replace this 2 by m. Okay, and m is going to become large, and this is going to become m over 2. Okay. And that's all you really need to do. So now we can take the exact partition function, which is an integral over c, integral over f alpha, of exponential minus the usual term, but let's just focus on the important term here, to be plus 0 to beta, gk over m. And let me write this as f dagger alpha, c0 alpha mod squared. And then I do my favorite trick of a Hubbard-Stratonovich transformation. So I add another field dp, which is just a function of time. And that will be m mod p squared over jk minus p times f0 alpha c dagger 0 alpha minus p star. Sorry. This is all awful notation. F alpha dagger, C0 alpha, C0 alpha dagger, F alpha. So all so far exact and very much paralleling the spin liquid. In fact, this is a much simpler case of the spin liquid. And in some sense, I should have done this before we went to spin liquids. But then we wouldn't have, the advantage of spin liquids, we don't have this gapless C to worry about, which is the C electrons. And now you can see that if I do the path integral over these two, I'm left, I get some action, which has an M out front. Okay, so after There's also a Lagrange multiplier. So I get the Z that is some pattern over dp, and a Lagrange multiplier d lambda of exponential minus m times some effective action, which is a function now of p and lambda. Here I have another term here, which is I lambda times f dagger alpha f alpha minus m over 2. Okay, all the details are in the notes. All right, so then you play the usual game and you look for the saddle point equations.
What happened to the first term in H?
I didn't write it out, it's there. There are various other things.
And when you integrate it out, the C's.
Yeah, there you certainly need all of that information to know what S effective is. But I'm not writing out explicitly because we can guess. What we really care about are the saddle point equations. P equals 0. So what are these equations? What form do they take? And I claim you can just guess, just you have enough experience with this, hopefully. We can simply guess what form these will take. Both lambda and P will have a time-independent expectation value. So the mean field equations that you get are the large and mean field equations. So you have some mean field Hamiltonian, which will, of course, have the first term. And then it will have the mean value of lambda bar times f dagger alpha. Well, yeah, okay. Minus m over 2. And P will also be replaced by a mean value minus P bar of C dagger 0 alpha f alpha. So beautifully, I just get a free fermion Hamiltonian at U equals 0. So there's no interaction. There's just some chemical potential for the F, and there's a hybridization P bar. So the difference from the original model, which if I just put U equals 0 in the original model, this will be some bare chemical potential. This would be W. But now this is not W. It's something non-trivial. It has to be determined by solving these equations. And so you have a self-consistency equation like in any Hartree-Fock theory. You have the equation that for the trivial one, f dagger alpha, f alpha expectation value is m over 2. But you also have the equation that P bar is 1 over m times the expectation value of f dagger alpha C0 alpha. Okay. So that's a very standard large M procedure. And we're back to the U equals 0 Hamiltonian, the Anderson Hamiltonian, except that the hybridization, as it's called, has to be determined self-consistently. Okay. And that's, in fact, all of the physics of the Kondo effect is in that self-consistency. That's where we find the logs and everything else. Okay. So, all right. So now we have to solve these equations, and in fact, most of them can be solved. And I'll talk about that next time. Let me just make one comment now. What about this gauge symmetry? So now, if I look at these new fields that I introduced, you can see that P, well, it's a scalar, so it's like a boson. And P also transforms under the gauge symmetry. Here I may have the convention here, I think. So P has the same transformation as F dagger. So P goes to E times e to the minus I phi of tau. Okay. So what's happened here is that in the saddle point, if there's such a saddle point that P bar is non-zero, then at that saddle point, I have the condensation of a scalar field, which is a charge under the gauge symmetry. So that's like a Higgs mechanism. So any non-zero value of P bar is telling you that you're in the Higgs phase, and then you can forget about the gauge symmetry, which is why people never talk about it. And the essence of the Kondo effect is simply the statement that no matter how small JK goes to zero, P bar is always non-zero. So you're always in the Higgs phase. That's the same statement as JK flows to infinity.
P is a quantum mechanical degree of freedom that lives at the point, right?
Yes, this is the saddle point. Yeah, there'll be fluctuations about it.
Right. So then the gauge symmetry shouldn't we average over the phase of P?
Yeah, or you can fix the gauge by, you can make lambda time, it's often easier is to make lambda time independent, and that fixes the gauge completely. Lambda is also transformed the gauge symmetry as a vector field. So lambda goes to lambda minus d phi d tau or something like that.
I mean,
So you have to fix the gauge in some way.
okay, maybe what confuses me is the fact that we have like a zero-dimensional problem with some Gauss law.
Yeah.
Normally we would impose that would impose that we have just singlet.
Yeah, well, I'm not sure how to answer that. Basically, I mean, there is a Gauss law, but this is the statement of Gauss's law that the density is fixed, okay? And you're not allowed to fluctuate. There's no charge fluctuation. This is basically Gauss's law here. This is the gauge charge is m/2, no fluctuations. And that Gauss law is imposed by the lambda fluctuations. But there's a gauge symmetry in the sense that if you try to do the path integral literally, you'll find various zero modes because of this symmetry. So you have to fix the gauge, and you can fix the gauge to make lambda time independent. And then the phase of P becomes physical, and it's involved in the 1/n corrections of various quantities. And it represents those fluctuations represent some of these other nosy effect I was talking about, various density interactions or spin higher order corrections to the fixed point, but it won't change the fixed point.
I think what Juan is asking about is that since you're in zero dimensions,
Yeah,
plus one dimension, there isn't really a meaningful Higgs versus non-Higgs.
yeah.
I think there's no Coulomb phase in zero dimension.
Right. So like I said, yes, I agree with that. Sure. I mean, this language, you can discard it if you don't like it. It's just a very useful language once you get to the lattice.
Maybe it's precise for large n, actually.
It is precise for large n, yes. Yeah.
But why is it precise for us?
Because large n is like infinite many degrees of freedom. So I'm just guessing, actually.
But they are all transform under the same phase. There's only one U1 that acts only on one side.
I mean, you can imagine a phase where P bar is 0, and even in this model. But that's a very ugly phase because in that phase, the JK has gone to 0, and you have a degenerate two-level system coupled to something else. So that's kind of a very trivial state with the degeneracy. So that never happens here. You can also get some more non-trivial fixed points, I guess, but not in this particular large n limit. There are more SYK large n limits you can take in some multi-channel problems.
I think I could say it more.
Yeah,
The procedure is that you pick a temporal gauge, which in this case is lambda equals constant.
yes,
And then you impose Gauss law.
yeah,
Then, or equivalently, when you fix that gauge, there's a remaining freedom, which is time-independent gauge transform.
right. So that's
In
it.
this case, but in this case, there are no time-independent gauge transformations.
No, if you're at finite temperature and you're integrating, you do have to integrate over the time-independent gauge transformations, and that will get you to the canonical versus non-canonical ensemble. And in fact, my only paper with Alexei Kitev, we do that in great detail for the complex SYK model where there's similar ratios. You do have to do this time integral of this thing or the circle, and that gives you answers either in the canonical, this is like the canonical ensemble, or the grand canonical ensemble where you fix lambda and not the density. But all of that, gives you higher order corrections we don't care about really. But fair point, yeah. I mean, this is really perhaps, the large M procedure and everything I've written down, all they put perfectly valid. The words I attach to them, you can discard them if you don't like them. But I find them useful once we get to the lattice model. Okay, thanks. You're giving a talk in 15 minutes, Edward, is that right?
I think it works, I think.
So here I checked with Tom, my memory of the history. And
Yes.
he confirmed that
Uh-huh.
the CPN on the lattice, say in 3+1 dimensions, was understood that it could give us a massless photon.
Okay.
When that was kind of this part in this language, it would be the partons. But so I learned that from him in the late 70s or very early 80s.
Okay, well, that's well before anything can does matter, so good to know that.
Yeah, what I don't know is the extent to which many people knew this.
Yeah,
And I'm not sure if I knew it, but never published it because it seemed totally trivial after the two-dimensional case.
I know, that's often the case, right? I mean, many things about,
And so I don't know exactly whether anybody put this in the paper. So
yeah, I've been in this sort of a similar, like in the, Z2 spin liquid and toric code. I knew all out of that. I didn't even think about publishing, and then it's become a big thing.
So,
Okay. Anyway, yeah, these things happen. When things are first discovered, you don't realize the significance.
No, the significance of this, I think, was I learned that.
Well, or
It's
how,
a very surprising.
how
thing,
it could be
it's not-
significant in other contexts, for example.
In the context of high energy physics, the fact that gauge symmetry is very fundamental.
I think what is true is that they exploited this to do real physics in a way that we never.
No, that's clearly the case. But it's often the case, the person who does the first thing doesn't understand, doesn't do 100% accurately, doesn't understand the full significance. And that's then somebody else does better. That's why there's progress.